All right. So, welcome everybody. Today's going to be a really exciting day because you know, even more exciting than last time. So last time we developed and showed Gauss's law. It's the thing that's going to make talking about electrostatics much easier. And as a first example, I used you know, figuring out what the electric field is of an infinitely large charged plane, and it turns out that you can do that very easily if you know exactly what the symmetries in the problem are in terms what that does for the electric field, and then you can simplify your flux integral. And that's really the name of the game when we use Gauss's law. And I'll walk you through a couple of examples of how you can do that and put Gauss's law to use. The thing that you should realize with Gauss's law is that so Gauss's law connects the flux with the electric field and the enclosed charge, and Gauss's law is always valid in electrostatics problems, but it's not always useful. So you can use Gauss's law really easily in problems with a really high degree of symmetry. And then it's useful in situations with not such a high degree of symmetry. It's valid, except you can't really use it to figure out what the electric field is. So in those kind of cases, you'll need to do the direct integration. All right, so with that intro out of the way, let me do the attendance, and let me pause this for a second. Okay, so yeah, so the other thing that I wanted to mention, so with Gauss's law, this normal, remember this is the normal, is always going to be pointing out, and it's pointing out of this Gaussian surface that is described by this integral. This is a surface integral, so usually if you wanted to do this explicitly, you'd have to integrate over two variables and maybe even set this up and do it over separate patches. And because the Gaussian surface is around a volume and it has a well-defined inside and outside, that normal is unambiguously defined. It's always pointing out. And then this arrow here, it's equal. I put this arrow here because I think it's important to show the causality. So this charge generates this electric field, and that's to make it look a little different from the other expression that you've seen with charge and electric field, which is the Coulomb force law, where you have an F is Q times E. In that case, the Q is placed in some kind of an electric field that doesn't necessarily have anything to do with the Q itself, because this electric field then would be externally generated. So that's not what this Gauss's law describes. Now, as I was saying before, this integral could be really tricky to evaluate, except if you figure out a way to shape the Gaussian surface such that there are big parts of the Gaussian surface where this electric field is constant, such that you can factor the electric field out and you're left with just a surface integral dA, so just E times whatever surface area is. And then on the right-hand side, you have a Q. So you solve for E, you get E as a function of Q, and you're done. So as the first example, we used this box, and I set this box up in such a way that there are 6 distinct surfaces. So there's here, let me get my nice box again. So there's 6 distinct surfaces, right? So top, right, left, bottom, top, I suppose front, and then back, right? So if you assume that the electric field lines go this way, then the only non-zero contribution to the flux is going to be through this face and then through this face. So therefore, this flux is going to be whatever the E field is here at this surface and the E field here at this surface. And if that's uniform, then the flux is going to be 2 times E times A. So that's what we do, so that E becomes factored out. And then right-hand side is the enclosed charge. That's the stuff that sits right here in this green patch. And that is the surface charge density sigma times whatever the surface area is enclosed here. And fortunately, that means that the area sits here and the area sits here. So these two cancel and we get E is sigma over 2 epsilon naught. So the hardest part in doing these problems is determining what shape to use for the Gaussian surface. So you want to use a shape that fits with the symmetry, and therefore, you could use a Gaussian surface here that's a sphere that's crossing the boundary. Gauss's law would be correct, but it would not be useful because this electric field can then not be factored out from your integral. So it's correct, but not useful. So so in a problem, I would give you a charged plane, and then you would have to determine what the right symmetry is, and then afterwards what kind of Gaussian surface to use. So let's do that, because I took a couple of shortcuts here. I immediately assumed that it was going to be pointing out and uniform. So so we'll look at the symmetry. So using Gauss's law, step 1, identify the symmetry. Sometimes plural. Choose Gaussian surface. I never know if that's supposed to be a capital G. Gaussian surface that fits the symmetry. Factor out E. And then you're done. So let's go back to the plane. So I'm not drawing the electric field yet, but I'm going to say this thing is charged. So we have a uniform surface charge density. For simplicity, let's assume that it's positively charged. Positive, positive. And it's uniform, which means that the spacing between these axes should be constant. And yeah, that's not too bad. And it's a thin plane, so thin plane. So in the limit of the thickness going to 0, it's infinitely thin. And it's also infinitely large. Okay, now these clues are supposed to be enough of a hint to determine what this electric field is going to look like. So the first is the thin plane. Because it's a thin plane, that means that there's the charge that sits on the surface here is immediately visible from the right side, but it's also sitting from the left side. It's really just a charged plane. And that means that there should be mirror symmetry, right? So the thing that's going on the right, if I flip the plane over, should be identical to the thing that's going on to the left, except it's going to be mirror imaged. The other thing that you should look at is the fact that it's infinitely large. So if it's infinitely large and it is otherwise completely uniformly charged and it has no features, there's no maps or coordinate system or anything like that. If it's infinitely large, it's going to look the same no matter how far you are away from Z, from the plane. So we assume, therefore, because it's infinitely large, that the electric field is going to be always the same here, and it's going to be independent of Z. And if it is independent on Z, that means that whatever field lines we're going to find here will always be parallel. So infinitely large, that means no Z dependence. And therefore, the field is going to be uniform. And if it's uniform, that means that the E lines are all parallel. Okay, now let's let's use some electric field lines. So we can draw them, if this is the plane, we can draw the field lines like this. These could be field lines that we have. These could be field lines that we have. Or these could be field lines that we have. Right, so you can take any one of these pairs and put them right here and then connect them all. So basically nicely fill out the space here. And this is on the right side of the plane. So then we would have to mirror it on the other side. And now the question is, which ones of these solutions is the right one to use? So I'm going to do the nearpot thing again. Give me a second. Okay, so we have 4 different versions of possibilities for what the electric field lines look like. So they're all in parallel. But if you look very carefully at this, you'll see that there's really only 2 solutions that matter. There's the blue one and the green one, and the red and the black are linear combinations of the blue and the green one. So we could talk about only the blue and the green one, or we could talk about all of them. So we can do all of them because it's good practice. So the let's say it looks like this. Okay, so now I'm going to draw the electric field as if the red solution is correct. Okay, so let's say field lines do this. Then, due to the inversion symmetry on the plane, the other thing should look identical. Now, because this plane is completely featureless and it's infinitely large, there's actually also a rotational symmetry, meaning we could take the plane and turn the whole thing over. And if we do that, so rotate it, so I'm going to try to draw a rotation, then the field looks like this. Now, obviously that's not the same. So therefore, this cannot be a solution for the electric field. And we could do the same thing for the green, right? So green solution, field like this, down. Sorry, I should draw them a little longer, down, and then inversion symmetry. This is the plane, same thing. If I turn it over, then these field lines that are pointing down, now they're pointing up. So this would become field lines in this direction, which is not the same either. So the symmetry says that there cannot be a preference for up or down. In other words, if it's pointing down and we rotate it and afterwards it's pointing up, that doesn't fit with the rotational symmetry. So neither the green nor the red one fit the symmetry. Now the black one is basically the same problem. So the only one that actually works is the blue one. So because if the plane is like this and the field lines are pointing like this, then if I rotate it, so again, like this, so then these field lines, they don't really move. They're staying the same. So this one fits. So we've used symmetry to determine what the electric field looks like. So this one is the one that fits, and therefore we have this. All right, now that's step 1 in applying Gauss's law, right? So we have identified the symmetries, and now we got to choose a Gaussian surface that fits with the symmetry. So the Gaussian surface needs to have an inside and an outside, so it's a hollow thing, and we need to figure out a way in which the flux going through surfaces is either constant or 0. So there are really only two solutions to this. We can build a box out of surfaces that are like this, and we can build a box out of surfaces that are like this. So if the normal for this is like this, and the normal for this is like this, these are really the only types of surfaces that we can use to construct a box, a Gaussian surface or a box that fits the symmetry. So you see this shape appearing already, and obviously that's the box that we had before. So on green surfaces, the normal is perpendicular to the electric field, so there will be no contribution to the flux on those parts of the surface. And here, the normal is pointing exactly in the same direction as the electric field. And the electric field, because it doesn't really change, is a function of z, is the same all across this surface. So therefore, our Gaussian volume looks like this box, right? So I'm going to make red surface here, red surface there, green, green, done. And obviously it has a front and a back, and the front here is like the green surface because field lines are like this, and then the normal on the front is like this, so that's also 90 degrees. So the final flux that we'll get is the flux total is going to be the red flux, fluxes through the red surfaces and fluxes through the green surfaces. All the fluxes through the green surfaces will evaluate to 0, so we only need the fluxes on the red surfaces. There's one on the left, there's one on the right, and again, the surface here on the top, and then behind, they're also green. So this flux is going to be whatever E is here at this surface times the surface area. Surface area we choose is A. So this is going to be 2EA. That is the left-hand side of Gauss's law. And now the right-hand side is going to be the included charge. And the included charge is all the charge that sits right here. And I had it in a three-dimensional drawing earlier. So in the three-dimensional drawing, it looks like this green surface, right? So if you do the cross section, then you get the surface charge is everything that's sitting here. And if that's sigma, then whatever the size is of that face times A is going to be the included enclosed charge. So that's going to be sigma times A. And then we need the epsilon naught from Gauss's law. And then you factor out your E, or in other words, divide by A. You get, finally, I apologize, I'm running out of space, sigma over 2 epsilon naught. Sigma over 2 epsilon naught. And I hope you realize how powerful symmetry is in this case. And it's very careful consideration of the symmetry that allows you to make use of Gauss's law in this case. All right, so that's Gauss's law for a plane. Now the other thing we can do is we can use Gauss's law for a sphere. So we already know what the electric field looks like, except we're going to try to forget it for now and see if we can determine what it is using only symmetry and Gauss's law. So here we go. I'm going to make this sphere. I'm going to make it, kind of large. All right, positively charged. In the end, whatever Q is, I'm going to call this Q. In the end, whatever Q is and whatever electric field we get, we can always figure out what the field is if we change the charge to something negative, because we just invert the sign of Q and then the field points the opposite direction. Okay, so this is so it's a perfect sphere, right? Perfect sphere. And uniform charge density Now, for now, let's just only consider the surface. So this could be a solid insulating piece of material that has the charge spread out over its interior volume, or it could be a metal where the charge sits on the surface, because we haven't really talked about, you know, electric fields and metals versus insulators yet. So I want to leave that point alone for now, and I only want to talk about the field from the outside. Okay, so step one, the symmetry. So we have, again, several things we can do. But we need to consider the symmetry that we have. So the first is that because this is a perfect sphere, we can have only a dependence on R in the electric field. So only R dependence is allowed because of the rotational symmetry, right? So if there will be an angular dependence, then we can always rotate the thing around by 100 degrees, and then that angular dependence would have to cancel because it would still be the same sphere. So we're only allowed to have an R dependence in the electric field. And if I draw, again, electric field lines, for instance, I could have the field lines pointing like this. And again, I would not be allowed to do that because I could take the sphere, turn it over, and then these field lines would be pointing, oops, these field lines would be pointing in the opposite direction. So you can't do that. So the only types of field lines that we're allowed to use are the field lines that point radially out. All right. Now, we knew this already, but it's always good to see that the symmetry tells you this is really the only thing you're allowed to do. Okay, so not only do we have only R dependence, we can also have only an R component. And R dependence and R components are important. Okay, now Gauss's law says that some kind of a enclosed charge generates a flux and that's the flux. So I'm writing it a little bit different, but I prefer writing it like this because then it's clear that this charge generates this field. All right. So step two in our Gaussian using Gauss's law problem is going to be, what kind of Gaussian surface do we pick? Well, we only want to make a box out of surfaces that have electric fields that are uniform over whatever patch we take, or electric fields that are normal to that surface that would therefore not contribute to the flux. So this thing becomes easy. So we have only this kind of surface where the normal is always pointing out, or we can build a box out of this. So in this case, we don't need the black type of surface because we can make a closed box using only surfaces of the type that are drawn in the red, which means that we can just draw a circle here, and that circle would then be the cross section for a otherwise three-dimensional problem. And now I'm running into my text, and I regret making this drawing so big. At every point here, my field and my normal are pointing in the exact same direction. So therefore, every time this dot product evaluates to E times dA times the cosine of 0. So in other words, it's just going to be E times dA. And in the same reason, because this sphere is at a fixed r distance, and we can only have an r dependence for the electric field, because this surface is all at the same electric field, it is constant over this entire surface. So therefore, this is epsilon naught times E times the surface of the sphere. So that's 4 pi r squared. That is going to be equal then to Q enclosed. So that's Q. So now we solve for E. E is Q over 4 pi epsilon naught r squared. And now finally, we want to make that into a vector, because electric field is a vector. And if you want to write it in the same way that we were using before, using K is 1 over 4 pi epsilon naught, then this becomes K Q r hat over r squared. Da-da-da, we are done. So this may look a little funny, because we used Gauss's law. Sorry, we used the sphere to derive, or some people would call that not derivation, but I think it's pretty solid, to derive Gauss's law, and now we're going backwards. So that might seem might seem a little funny, but I hope you realize that Gauss's law working backwards is way more powerful than a sphere working forward. So Gauss's law is a really good way to start these problems, even if you already know what it looks like. So that's for a perfect sphere. Now there's another example, and fortunately with Gauss's law there's only so many situations that you can use. So you can sometimes even memorize what the symmetries do and what they do. So so I'm going to make a drawing. This is a so it's a cylinder. So it's oops, infinitely long cylinder, uniform charge, and the assignment is, what is the electric field? So this thing keeps going, right? So it keeps going in this direction, keeps going in this direction. And now the question is, what does the electric field look like? So I'm gonna draw this. Let me see. I'm gonna draw this in a little bit, but first I want you to try this. So the question is not only what's the electric field, but also draw the field lines. So this is your assignment for now. So draw the field lines, and I will do the thing again. So most of you got this correct, so that's good. So first part of using Gauss's law, we have to work with the symmetry of the problem. So becomes a little bit tricky to draw these field lines. So let me just call this the z direction, call this the r direction, and then phi is basically the thing that allows you to rotate. And the z-axis is right in the middle here, okay? So we have translational symmetry in the z direction, so we could pick any point here and then move it this way, and the field cannot look different. We also have rotational symmetry, right? Because we can rotate the cylinder around and would still be the same field. So if I draw a cross section of this situation, I'm going to draw a cross section. Let's say, so look at it from this side, then I get this. Now, in this case, Z is pointing, in or out, doesn't really matter. R is in this direction, and phi is in this direction. I believe I got that right. Yes, phi is in this direction. So now we're doing the same thing again. We can decide to draw field lines that are in the phi direction, or in R direction, or something in between. So, for instance, this field line and this field line are not allowed, because when I rotate the cylinder around, these things are pointing down. So this type, oops, I'm running out of colors. This type of field line is allowed because when I rotate this thing around, the configuration of the electric field does not change. Now, there is another field line that you could draw, and that's circular field lines. So black ones. Oops. And those are obviously not allowed either, because when I turn this thing around, I cannot only rotate it, but I can also invert it, right? So I could take this wire and then move it upside down. Then this down arrow becomes, this up arrow becomes this down arrow, and obviously that's not allowed either. So really the only kind of field line that you can have is pointing radially out. What we did not discuss yet is the component in the Z direction. So therefore, I'm going to use another drawing. So I'll draw this like this. So this is the cylinder again, but now it's a cross section. And again, we can draw field lines. We already know that they're pointing up, but could they be pointing in this direction? And the answer is no, because I could take this wire, if it's like this, and then the field lines are attached to it, and I flip it around. Now they're pointing in the opposite direction, and that's not allowed. So in the end, we are left with field lines that are only doing this. All right, so we get only an R dependence and only an R component. Right now, that could be a distinction without a difference, but when we start doing magnetic fields, this becomes important, that we make a distinction between R dependence and R component. Okay, so the only ones that we're allowed to use are ones that are pointing radially out. So let me see if I can draw that. So down, down. Oops. All right, and then here as well. All right, so they're pointing exactly in the plane that is perpendicular to the wire. And now step 2 of Gauss's law is, okay, let's build our Gaussian surface. So in order for that to be useful, we can only build it out of surfaces that are perpendicular or parallel. So we could build our surface in patches that are following the field lines. So for instance, it would be here, and then it would be here, would be a patch. That's one type of surface that we can use, so it rotates with it. And the other we can use is a patch that sits perpendicular and to the field line, so the normal points in this direction. And these are the only two types of surface segments that we can use. So the box that we built with this is a Gaussian surface of a cylindrical form. So we take a black type of surface on this end, a black type of surface on this end, and in between there's a cylinder made of putting all these red stitched areas together, and it looks just like a cylinder. So it would go around here. So after all this drawing, let me draw this because it's going to get a little messy. Might as well. Okay, so the Gaussian surface does this. So this is the front face. This is behind. Sorry, this goes behind here. So that's what it looks like. So a perfect cylinder, more perfect than I drew it. And we have a contribution to the flux of the red types of surfaces that are sitting here on the cylinder wall, and a flux going through the black type surface which sits on either end. So finally, two-line derivation, flux, total flux in Gauss's law is this one, and I'm getting a little crazy with the color coding. Oh, it's not green. See, I'm confusing myself. It's black. Okay, so the field lines here are perpendicular to the surface. So this flux is 0. The red flux is all we've got. All right, so that's going to be E times whatever the surface area is. Okay, so let's call this a box of length L. And we already have an R. So the surface area of this is L times 2 pi R. So 2 pi R L. So that's the flux side of Gauss's law. And now we want to know the enclosed charge. Well, the enclosed charge is a little bit tricky because it's whatever the charge density here is in this box. We can call the charge density linear. So for instance, because it's a linear problem, we can say, okay, there's a certain amount of charges per length. We can do it this way, or we can work with surface charge density. Either one is fine. I'm going to use lambda because it is a rod. So the enclosed charge, Q enclosed over epsilon naught. The enclosed charge is lambda times L, and then the rest is Gauss's law at work. So therefore, the electric field is lambda 2 pi epsilon naught R, and it's in the R hat direction. That's important. I again ran out of space, but I hope you see that works. So that's the charge of a cylindrical object. Only depends on R. There's no phi dependence. Points out radially in the R hat direction, and that's the thing. Something about my cylindrical coordinates, by the way. I sometimes mix up my little r's and my big R's. In this case, I don't think it's ambiguous. Some people in cylindrical coordinate systems use a rho for the R component to distinguish it from the position vector, which has not just the rho, but also the phi and the z component. For now, let's just ignore that. But that's just a tricky thing to pay attention to. So that's the cylinder. So there were two important points raised. Like I was saying before, I switched my big R to little r mid derivation. It's sloppy. I don't recommend you do that, and I apologize. The second is, where did my lambda come from? So I want to make a note about the infinities. So this rod is uniformly charged, but it's infinitely large, which means that the charge that sits on the rod itself is infinitely large. And we can't really work with infinite charges in Gauss's law, because then we would have an infinite field, but it makes no sense. So the thing that makes it finite is talking about charge densities. So in this case, we had a rod that was large, had an infinite charge, but a finite charge density. So therefore, we end up with a charge density in the problem. And we could use lambda here, but we could also use sigma. So sigma would then be the surface charge density of the rod, or we could even use rho if you want to, if it's sitting throughout the whole volume. But for both sigma and rho, you would have to know what the size of the rod is, and I didn't want to introduce another variable in the problem. Both are fine, but it's not necessarily useful to do that unless you have something specific to say about the nature of this rod, and I will talk to you about that in a little bit. Now, the same thing happened with the plane, right? So when we had a plane, this plane was an infinitely large plane, and the charge density was finite though, right? But we can't really have infinite electric field, so somehow we need to put the surface charge density in there. And in fact, that's what we did. We said the enclosed charge is the surface charge density times A. So also in this case, because the total charge is infinite, we end up with E field that depends on the charge density. And now finally, this one is the only one that was not did not have an infinite amount of charge, because the object is finite. So therefore, the total charge shows up rather than our needing to use charge densities. You can if you want to, but you don't really need to when it comes to these kind of problems. All right. So I want to make one more comment about symmetry. So you have to be really, really careful when you use symmetry. So when so I'm going to go back to my cylindrical charged problem. So I'm going to draw my little charged object here. All right, and let me just draw a couple more field lines, otherwise it looks so lonely. All right, so this is my charged object. I got some Q. It's positively charged again, because why not? And now I am going to do something that I'm not allowed to do. So I'm going to put a Gaussian surface that is a sphere. And remember, I made a whole point of saying that, well, we have spherical symmetry, so we're allowed to use Gaussian surfaces that are spheres, except I'm not putting it around the charged object. I'm actually putting it offset. And now, if you want to be really super fast, you could say, well, you know, I got no enclosed charge, because the charge is sitting here outside of the box. So because I got no enclosed charge, flux is Q over epsilon naught is the integral of E dA. And you know, we have spherical symmetry, so this is just E times whatever 4 pi r squared this box is, so I'll call that R. And because Q is 0, E is 0. Yay, except no, you're not allowed to do this. The question is, why not? Well, we didn't really use the symmetry correctly, because it's only symmetric for spherical objects that are sitting at the same R from the center of the structure. Or put it another way, there is a finite flux that goes here that is negative, because here the electric field lines go in. And then there's a flux that goes through the green surface here that is positive. So this one, flux is positive. This one, flux is negative. And because the enclosed charge is 0, both of these are going to add up to a net flux of 0. So indeed, the flux is going to be 0 because the enclosed charge is 0, but that does not imply that the electric field is 0 because the electric field is not the same at this point compared to this point. So be very careful with these symmetries. All right. Next thing, let's talk about conductors versus insulators in electric fields. So conductor in an E field and an insulator in an E field. Oops. So in this class, we'll only make a distinction between conductors and insulators, but sometimes that distinction is not as easy to make because certain insulators, if you apply enough electric field, actually become conductors, and in that case, they're called semiconductors, and vice versa. There are so this line does not need to be as sharp as it needs to be. But for now, let's assume ideal conductors, ideal insulators. So a conductor in an electric field and an insulator in an electric field are very different animals. All right, so I'm going to draw the initial configuration. So I'm taking some kind of an E field, and let's, for simplicity's sake, make this a uniform field. And now I'm going to place a conductor in this field. So this is going to be my conductor, and I'm going to make this thing a sphere. And let's assume that it's a perfect sphere. And now the question is, what's going to happen to the sphere? Because the sphere, the sphere is, let's say, initially neutral. I'll call this initially neutral. Initially neutral. This sphere consists of some kind of a lattice that holds charges confined to the box, but within the box or within the sphere, they are free to move. So in other words, there are charges that are sitting on the surface here that will see this electric field right at that surface. And because the electric field here is pointing in a direction along the surface, charges will be free to move. And if they're positive charges, they'll be forced in the direction of the electric field. And if they're negative, they're going to go in the opposite direction. So you'll end up with a situation, and this is a process that's going to happen real fast. So I'm going to just draw this as a sphere. I will make this thicker in a little bit, but the electric field lines will do this. And that means that this side of the sphere became negatively charged, and this side of the sphere became positively charged. So the positive charges were pulled in this direction, right? So imagine you're a charged object here, you're sitting right here, and you ask yourself, what is my force? And you'll see that if you're sitting right here, you're going to be dragged in this direction. So the positive charges go there. And whenever you move a positive charge from here to the other, it's going to leave a negative charge there because the object was neutral to begin with. And you'll end up with all the positive charges there and the negative charges over here. And this process of going from here to there is going to keep repeating until equilibrium is established. And what is the equilibrium condition? So equilibrium means charges not moving. If the charges are not moving, then we have an equilibrium situation. So what's the relation between the electric field and the charge that would cause them not to move? Well, it would be as long as there is a net force that is acting on these charges at the surface, it's going to move to a different location. And if that force has a component along the direction of the surface, that means that the charge is going to move. So it's going to keep moving until that component that is tangential to the surface vanishes. In other words, it keeps going until the electric field is perpendicular to the surface. And I didn't really draw it very well, but the E field is perpendicular to the surface of a conductor. All right, that's a very important thing to remember. The next thing that I want to talk about is insulators in an electric field. So insulators, let's say, start with the same situation, uniform field. And now I'm going to place my insulating sphere in here. What's going to happen? Well, there are no mobile charges in this sphere, but inside the sphere there are, negatively charged electrons that are free to move a little bit around the positively charged nucleus. So they're definitely going to see this electric field, and what you'll get is you'll get a field that looks a little bit more like this. So it's a little bit bent. And there's going to be negative charges here everywhere. And there's going to be positive charges everywhere as well. Except the negative charges spend a little bit more time on this side of the sphere than on that side. So you could say that this could be seeing a little bit more plus than this could be seeing a little bit more negative. So the effect is not as dramatic as for the conducting sphere. Now, the final thing is charges are always at the surface of a conductor. And if the charges are always at the surface of a conductor, that implies that the E field is 0 inside a conductor. And I'll show you how that works in a little bit. Now, this first statement actually comes from the following. So if you're charged, if your object is charged, then the way to minimize the Coulomb energy between these charges is by having all the charges sit on the surface. So it minimizes the energy, so therefore, if it sits on the surface, that's the lowest energy configuration. If we have that, then afterwards it follows that the electric field is 0. Okay, for this statement, we need Gauss's law again. So we have a charged sphere, so let's call it like this, and we can put our Gaussian surface here. We could also put it here. If we put it in the red location, then the Gauss's law is evaluated exactly like what we were doing before. If instead we're using the Gaussian surface inside the sphere, then spherical symmetry dictates that it's going to be, the flux is going to be E times 4 pi r squared, where r is just whatever radius this object has. But because the enclosed charge is 0, because all the charge sits on the surface, the electric field is 0. So Q enclosed is 0, implies that E is 0. And then here, E is not 0 unless this thing is not charged. All right, that's number 4. Now, number 5, and this is a puzzle for you. So, can you come up with a configuration of charges in which there is a stable equilibrium for a test charge. And let's go back to the activity, and I'm going to do the drawing. And it's just a white canvas for you to work with. All right. Well, let's go over a couple of interesting cases. So, for instance, but before I do that, let me remind everybody that what stable equilibrium means, that if the position, if the object, this test charge, is at rest and it was kicked to the side a little bit, it will be returning to its equilibrium position. So, for instance, in a potential energy landscape as a function of distance, what that means is that there is a minimum here. So you have an object that sits here. Whenever you try to kick it, the potential energy goes up a little bit and it returns to the initial configuration. So that's stable. This is unstable. So that's stable. This is unstable. And then there's also metastable, where you just have like an inflection point. Metastable, stable, unstable, metastable. Okay, so we want something of this kind. So let's start with the charge here. So this is my test charge. Now, if I put this thing in any kind of uniform field, then it's going to just start moving. So uniform fields are out. So that's definitely not a solution. So the next thing we need to think about, if it's not uniform, that means we need to figure out some way to position charges around here to make this thing stay in place. So if, for simplicity's sake, let's call this thing positive. All right. Then what we could do is we could take negative charges around it. So negative, negative, and we could spread it all around. And in this case, this would be an equilibrium condition, because all of these negative charges, if we take an infinite number of charges, all of these charges would be pulling equally hard on this charged object. So therefore, the net force would be 0. Except the problem is, as soon as it's kicked off to the side, it goes and slams into this charge, because all of a sudden, when it gets closer to this thing starts pulling harder and this thing starts pulling softer. So actually, you will accelerate and will go that way, and that doesn't work very well. So, well, what happens if we try positive configuration? Well, let's make them positive. So now it's being repelled by this. Now the question is, would this be stable or unstable? All right, so this is a trick question, right? So this kind of situation would work because, you know, all of these electric fields would do this, right? So then it's being repelled by all of these electric field lines, and that would be stable equilibrium, right? Because you could displace this thing and off to the side, and then it would be repelled a little bit more by this side than it would be by this side, so it would be pushed back into the center. All right, so what is wrong with this configuration? Well, Gauss's law says that you can't do this because I'm going to take a Gaussian surface, so I'm going to put this here, and I'm going to put it around it. And now Gauss's law says, because it's really nicely spherical symmetric, right? I have no test charge. The test charge is not there. We only put that in the moment we are happy with the configuration of the charges. And now Gauss's law says, you know what? You got a net inward flux. And you can only have that if you have a charge here. You cannot have this if you have a charge sitting in the surface. So the only way to get this kind of a charge, the only way to get this kind of a flux is by sticking a negative charge exactly at the center, exactly at the location where afterwards we want to put that little positively charged particle. So this field configuration is highly illegal. You can't do this unless you stick a negatively charged object there. There's no way to do it. So this is something where Gauss's law is way stronger than your intuition, right? Because when you draw this, you go like, you know what? This seems perfectly reasonable to me, and of course I can arrange positive charges this way. Except these field lines will not be pointing in because they will only do that if there's a negatively charged object here. All right, so the answer is nope, cannot be done. And this is a there's a generalization to this thing that's called Earnshaw's theorem. And Earnshaw's theorem talks about stable equilibrium in external fields. So for instance, it's a very generalized theorem, doesn't just apply to electrostatics, it also applies to gravity, and it applies to magnetism, with one caveat. And that is that when it comes to magnetism, Earnshaw's theorem doesn't always work. And there's a very famous example for this exception to this rule. And I'm going to see if I can change the screen. So what you're going to look at now is a very strong magnetic field. And that's a floating frog. And that's another floating thing. So the reason this works is that actually biological things are diamagnetic, and I will not explain diamagnetism to you, but what I want to say is that this thing works really well for very classical theories, but diamagnetism is a consequence of quantum mechanics. Quantum mechanics therefore says you can do it. This floating frog is, by the way, is a famous example. Look up the YouTube videos. Interesting story. This work was done by Andre Geim, who ended up later discovering graphene. Got the Nobel Prize in Physics for it, and graphene is one of the things that I use in my lab a lot. Let me pause the recording and then ask if there's any final questions before we break.